Okay, this is going to be the lecture over section 18.5. We're going to continue to discuss capacitors and how they behave in general. You saw in section 18.4 that we went over the summary already, and we've discussed parallel plate capacitors and how the capacitance is tabulated. Now we're going to look at capacitors that are in sequence or in series as well as in parallel, and how can we go through and add those together. Again, you see the summaries here if these are in series, and you see them here as if they are in parallel. When we are talking about capacitors, again, we're talking about a plate here that has a certain area. Um, and they have a certain distance here. Remember that a capacitor is basically two conductors that are separated by a certain distance. So let's go to section 18.5 and let's kind of flesh this out a little bit. So what you're going to see here is a schematic of a series connection of two different capacitors. These are in series. Now, what do we mean by that? A series of capacitors is something that when we go from one path or one point in a path to another, that we go through one capacitor, then another, potentially more than that. But for right now, let's just discuss two. So this is going to be the route in which the potential difference is going to be measured, and we're going to have a point right here in between these two. Now, we're going to measure a particular potential difference here, which is going to be called V, or V sub AB, for the points at which it goes through. What you're also going to notice here is that the potential difference here is going to be the sum of the potential difference from here to here, which is noted as V1, and then from here to here, that's going to be noted as V2. So again, potential difference between both of those is going to be the sum of the first part and then the second part. Each of these capacitors is going to have the same charge Q. So whatever charge is built up here is going to be equal and opposite in charge of what builds up here, and the same thing is going to happen here. Now, let's kind of go through some of the verbal description here. Initially, these capacitors are uncharged. Then the potential difference is applied between those 2 points. Then the top plate here is going to acquire a positive charge, Q, and the electric field of that pulls negative charge up to the bottom plate. And once that happens, that negative charge has to come from here. So then you see a positive charge that's created here, and then a negative charge that's created here. So initially, when you add all of those together, you get 0, which essentially is what you had before. But now, since the potential difference is applied, you can see how those charges are being created. And since this is affecting this in terms of how much charge is being applied here, you can kind of see why those are going to end up being equal to each other. Now, when you do that, you can model this in such a fashion that rather than just having two or potentially even more capacitors in the sequence there, you could model this as if you just had one capacitor here that's in between those two. Now, the question comes about, how do you model this, and how is this equivalent to what we see here? Well, if you look at the equivalent capacitance here, again, that's going to be Q divided by V. If you look at the overall equivalent capacitance, this is going to be how you tabulate that, 1 over C1 plus 1 over C2. To get that, what we're going to be looking at here are the applications of these formulas and then the theory as to how that comes about. You see the voltage here from A to C is going to be equal to V1. We'd already defined that up above, and that's Q over C1. And then you can see the voltage from C to B is going to be V2, and it's going to be the same charge, which we'd already discussed, divided by C2. Since the voltage here is going to be equal to the sum of those, all we're doing is replacing that with these. So when we go through and do that, we can factor out the Q because it's the same quantity. And this is what we're left with here. Now, if we were to take this voltage and we're going to divide it by Q, and we do the same thing to this side of the equation, we see that the voltage divided by the charge is going to be equal to the sum. We go through and we replace this with the equivalent capacitance, and lo and behold, this is where the formula comes from. And if you have several different capacitors in a series, you can extend that formula because the logic is going to hold. Now, notice here that the equivalent capacitance is in the numerator, and the way that we account for that is to take all of this and put it to the -1 power. Notice that your units are going to be in farads. The magnitude of the charge is the same on all the plates of all of the capacitors, as given by this. Potential differences or voltages across the individual capacitors are in general different, and the equivalent capacitance is always less than the smallest capacitance in the combination. Now, that's if they're in series. Now, what happens if they're in parallel? If they're in parallel, you're going to have a pathway in which you just go through one capacitor and another pathway in which you go through a different capacitor. Now, in parallel, the capacitors are going to have the same potential. The charges, however, are going to be divided up a little bit differently. So Q1 is going to be equal to the capacitance of 1 times the voltage. Now the voltage is going to be the same. The charge here for 2 is going to be equal to the capacitance of 2 multiplied by the voltage. Again, the voltage is going to be the same. So if we were to build an equivalent capacitor to model that situation, the charge is going to be just the sum of each of those. The equivalent capacitance is going to be the sum of each of those. Now, again, going through the theory here, we've got the total charge is equal to the sum. We know that the charge is going to be equal to the capacitance times the voltage being the same in each case. We just factor that out, and we're left with the sum of the capacitances. We know that this is equal to the total charge divided by the voltage. We do the replacement here. Boom, we got the formula. For capacitors in parallel, this is going to be your general formula. Now, you're going to have several problems here in which you can go through and work through that. A lot of this stuff is spelled out here for you. I would encourage you to go through and to look at that.